The first law of thermodynamics indicates that any processes that satisfy the conservation of energy before and after the processes are attainable. However, those attainable processes are not always spontaneous. The second law of thermodynamics allows us to differentiate the spontaneous processes from all the attainable processes. In order to describe the second law, we will use a new thermodynamic property called entropy. The entropy of a system is a measure of the degree of randomness of the system, and it is associated with the dispersal or spreading out of energy. The concept of entropy is extended to the third law of thermodynamics, stating the entropy of all perfect crystalline substances is zero at absolute zero, or 0 Kelvin. Chapter 3 focuses on the significance of entropy of a system, and we will learn a variety of applications of entropy in this chapter. Spontaneous changes occurring in nature do not require work to bring about the changes. Entropy is a measure of the degree of randomness, and it will be used to determine the direction of a change. Entropy is defined thermodynamically by the heat transferred reversibly divided by temperature T. A sizable change of entropy is written by Q reversible divided by T, and the infinitesimal change of entropy is written by dQ reversible divided by T. Take note that the T here is the absolute temperature. Spontaneous changes in nature are directional, and they proceed in the direction of dispersing energy or matter randomly. This is an example of a spontaneous change, the spontaneous cooling of a hot object to cold environment. TH represents the temperature of the hot rectangular object, and Tc represents the temperature of the cold environment. The animation illustrates the spontaneous cooling of a hot object to the cold environment until the temperature of the hot object becomes equal to the temperature of the cold environment. The question is, why is the cooling of a hot object spontaneous? It can be answered in the perspective of the increase of total entropy that is associated with the cooling process. The animation on the left can be simplified by this chart. The hot object can be interpreted as a heat reservoir, and the cold environment can be interpreted as a cold sink. Heat Q is transferred from the heat reservoir to the cold sink. Delta S1 represents the entropy change of the heat reservoir after the loss of heat Q, and delta S2 represents the entropy change of cold sink after the gain of the same quantity of heat Q. Delta S1 is equal to negative Q over TH. Keep it in mind that the negative sign is used here because the heat reservoir lost heat Q. Delta S2 is equal to positive Q over Tc. The positive sign is used here because the cold sink gained the same quantity of heat that the heat reservoir lost. The total entropy is simply the sum of these two entropies, which is further simplified to Q times 1 over Tc minus 1 over Th. Since Tc is less than Th, 1 over Tc minus 1 over Th is positive, leading to positive delta S total. Positive delta S total implies the cooling of a hot object is spontaneous. We may use a spontaneous process to do work. A heat engine can be placed between the heat reservoir and cold sink. An engine acts as the system, and the heat transferred to the engine is denoted by QH. Take note that 100% of heat from the heat reservoir cannot be converted to work. Instead, only part of QH is converted to work W, and the remaining heat QC is wasted to the cold sink or cold environment. Be aware of the signs of QH and QC. The signs of QH and QC are based on the system or the engine. Since the engine gains QH, the sign of QH should be positive. On the contrary, the sign of QC should be negative because the engine loses QC to the cold sink. As long as the total energy remains the same before and after a change, the change is permissible. It is based on the first law of thermodynamics, or the law of energy conservation. However, not all attainable changes are spontaneous. The second law of thermodynamics allows us to identify the spontaneous changes from all attainable changes. The second law states that the total energy of an isolated system tends to be dispersed randomly. In other words, the total entropy of a system should always be positive for a spontaneous change. Examples of spontaneous changes are bouncing a ball when it is dropped to the ground, gas that spreads out, rusting of iron, etc. Entropy is defined statistically by K times log W. K is the Boltzmann's constant, and capital W represents the number of possible ways of arrangements called microstates. The statistical definition of entropy comes from the idea that a perfectly ordered crystalline solid has only one microstate. Suppose each unit of the crystalline solid is made by binding two atoms that have different electronegativity. Each unit of the perfect crystalline solid has only one way of arrangement. Log 1 in the perfect crystalline solid is 0, which leads to the entropy being 0. Suppose you have a disorderly solid that is made of one unit. As you can see, there are only two ways of arranging the unit. Consequently, the number of microstates is 2. How about a disorderly solid that is made of 2 units? There are 4 microstates, or 4 different ways of arranging the 2 units. Each one of the 2 units has 2 different ways of arrangement. So, capital W is equal to 2 times 2, or 2 to the second. This can be extended to an n-unit disorderly solid. Capital W is equal to 2 to the nth power. The entropy of the solid would be K times log 2 to the nth power. The power n can be brought to the front, which leads to nk times log 2. Since n, k, and log 2 are not zeros, the entropy of a disorderly solid is not 0 either. On the contrary, the entropy of a perfectly ordered crystalline solid is 0 due to the presence of only one microstate. How would entropy changes as a gas undergoes a volumetric expansion from volume initial to volume final? Let's find out. Take note that the number of microstates is directly proportional to volume. It implies that as the volume of a gas increases, the number of arranging gas particles also increases. This relation can be expressed capital W equals CV. The C represents a proportionality constant. Suppose there are n gas particles in the system. The number of microstates before the expansion is W1 times W2 times all the way to Wn. Plug W into the equation, which leads to CV initial to the nth power. Likewise, the number of microstates after the expansion is equal to CV final to the nth power. The entropy change delta S is S final minus S initial, which is equal to K times log W final minus K times log W initial. Plug these into the equation, which would lead to this. The exponent n can be brought to the front, and nk can be factored out like this. The delta S can be further simplified to nk times log V final over V initial. Nk is positive. Since V final is greater than V initial in volumetric expansion, log V final over V initial is positive. Consequently, delta S for the volumetric expansion of gas is positive. It implies that the expansion of gas brings about the increase of entropy. Scientists and engineers in 19th century tried to maximize work out of heat engine with a given quantity of thermal energy. Sadi Carnot was a French engineer and physicist. He published a book, The Reflection on the Motive Power of Fire, and described the maximum efficiency of heat engines. He is well known for Carnot cycle. I will prove that entropy is a state function by using Carnot cycle. Engines like automobile engines undergoes a cycle of 4 steps: fuel intake, compression, ignition and expansion, and exhaust. Basically, the work generated by an engine is a result of the heat released in a combustion process. In the previous chapter, we have seen that the PV curve under an isothermal condition is different from the PV curve under an adiabatic condition, as you can see in this picture. The curve adiabat is steeper than the curve isotherm. The Carnot cycle consists of 4 reversible steps: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The first step is a reversible isothermal expansion, which is represented by a red curve in the PV plot. It is a volumetric expansion from state A to state B under a reversible isothermal condition. The engine cylinder is expanded as heat QH is transferred into the cylinder. Since it is an isothermal process, the internal energy change in this step, delta UAB, is 0, which implies QH plus WAB is also equal to 0. It further implies that WAB equals negative QH. WAB can be written as negative integral from VA to VB PdV. Utilizing the perfect gas equation, P can be replaced by nRTH over V. The nRTH is a constant as a whole, and it can be brought out of the integral. Now, the work WAB can be expressed as negative nRTH times log VB over VA. The second step is a reversible adiabatic expansion, which is represented by a blue curve in the PV plot. It is a volumetric expansion from state B to state C under a reversible adiabatic condition. The temperature at state C is T cold or Tc. Since it is an adiabatic process, Q equals 0, implying that heat is not transferred into or out of the system. The internal energy change in this step, delta UBC, is equal to WBC because Q is 0. The internal energy change under an adiabatic condition is equal to heat capacity at constant volume CV times the temperature change. Consequently, delta UBC is equal to CV times Tc minus Th. The third step is a reversible isothermal compression, which is represented by a new red curve at the bottom in the PV plot. It is a volumetric compression from state C to state D under a reversible isothermal condition. The engine cylinder is compressed as heat QC escapes the cylinder. Since it is an isothermal process, the internal energy change in this step, delta UCD, is zero, which implies QC plus WCD is also equal to zero. It further implies that WCD equals negative QC. WCD can be written as negative integral from Vc to Vd PDV. Like we did at step 1, WCD can be expressed as negative nRTC times log Vd over Vc. The last step of the Carnot cycle is a reversible adiabatic compression, which is represented by a new blue curve in the PV plot. It is a volumetric compression from state D back to state A under a reversible adiabatic condition. The temperature at state A is Th. The internal energy change in this step, delta UdA, is equal to WdA because Q is zero. Like we did at step 2, delta UdA is equal to CV times Th minus Tc. The sum of work done in this cyclic process is WAB plus WBC plus WCD plus WdA. The work done at the first two steps is associated with expansion. It implies that work is done by the system to the surroundings. The work done at the last two steps is associated with compression. It implies that work is done by the surroundings to the system. The sum should be negative, meaning that the system does work to the surroundings during the cyclic process. Now, let's focus on the two adiabatic processes, adiabatic expansion from state B to state C, and adiabatic compression from state D to state A. In the previous chapter, it was derived that under an adiabatic condition, Tv to the power of gamma minus 1 always remains constant in any state. Take note that the gamma is the ratio of heat capacity Cp to the heat capacity Cv, or simply Cp over Cv. The relation can be applied to the adiabatic expansion step from B to C. That is, THVB to the gamma minus 1 at state B equals TCVC to the gamma minus 1 at state C. Now let's move to the last adiabatic process, that is, the adiabatic compression from state D to state A. Like we did at step 2, THVA to the gamma minus 1 at state A equals TCVD to the gamma minus 1 at state D. By manipulating these two equations, we can derive VA over VB equals VD over VC. We will use this equation for the upcoming derivation. The total heat transferred during this cyclic process is the sum of QH and QC. Plug these into the equation and it will lead to nRTH times log VB over VA plus nRTC times log VD over VC. Use the relation that was derived just before, and VD over VC can be replaced by VA over VB. The second term, positive log VA over VB, can be written as negative log VB over VA. The NR and log VB over VA can be factored out, which leads to NR times TH minus TC times log VB over VA. The total work done during this cyclic process is the sum of WAB plus WBC plus WCD plus WDA. Plug all of these into the equation, and it will lead to this. The second and fourth terms are cancelled. Like we did previously, VD over VC can be replaced by VA over VB. The negative NR and log VB over VA can be factored out, which leads to negative NR times TH minus TC times log VB over VA. This is a brief illustration about how a heat engine is working in correlation with Carnot cycle. The engine is the system that we carefully look into, and the PV plot represents the progressive change of pressure and volume of the engine cylinder. Heat or thermal energy QH is transferred into the engine from the heat reservoir or hot source. This is caused by combusting fuel. As a result of that, the engine cylinder expands and the pressure inside the cylinder drops, which is illustrated in the PV plot. The volumetric expansion causes the engine to perform work on the surroundings. The remaining unused heat, QC, escapes to the surroundings or cold sink. The engine returns to the initial state by taking in fuel and prepares for the next cycle. The sign of heat QH is positive because the system gains the heat QH, but the sign of heat QC is negative because the system loses the heat QC. In the previous slide, it was derived that the total heat transferred during a single cyclic process is NR times TH minus TC times log VB over VA, and the total work done by the engine during the cyclic process is negative NR times TH minus TC times log VB over VA. The total energy change during the cyclic process, delta U, is Q plus W. Plug this into the equation, which leads to the cancellation of both Q and W. Consequently, delta U is 0. It implies that the cyclic integration of state functions like internal energy U is always 0, which makes sense because a state function depends only on the initial and final states. And in a cyclic process, the final state of the previous cycle happens to be the initial state of the present cycle. The maximum work generated by the heat engine can be expressed as the absolute work, which is equal to QH plus QC. Take note that the QC is negative while QH is positive, meaning the sum of QH and QC is less than QH, which is equal to the maximum work done by the engine during the cyclic process. And it is equal to NR times TH minus TC times log VB over VA. The efficiency of the Carnot engine is denoted by epsilon, and it is the maximum work performed by the engine divided by heat absorbed by the engine. It is expressed as the maximum work over QH. The maximum work is equal to QH plus QC. Consequently, the engine efficiency is QH plus QC over QH. Plug the expressions for QH and QC that were derived in the previous slide. the nR and log VB over VA are cancelled, which leads to TH minus TC over TH. It is simplified to 1 minus TC over TH. Since TC over TH is positive, the engine efficiency is less than 1. The engine efficiency value 1 indicates that 100% of heat transferred into the engine is converted to work, which can never be realized by all means. The only way to bring the epsilon close to 1 is only when Tc becomes close to 0 Kelvin and Th becomes infinitely high. Thus, heat can never be totally converted to work, even in a reversible process. In general, all reversible engines have the same efficiency regardless of their construction, which is always less than 1. And irreversible engines have lower efficiency than reversible engines. The engine efficiency epsilon can be expressed with respect to the heat gained and lost. It can also be expressed with respect to the temperature of heat reservoir and the temperature of cold sink. So, the epsilon can be written as QH plus QC over QH equals TH minus TC over TH. The equation can be simplified like this. 1 is cancelled, and the Q's and T's can be rearranged like this. Move negative QH over TH to the left side of the equation, which leads to QC over TC plus QH over TH equals 0. What is the significance of this equation? It implies that the sum of Q over T in a single Carnot cycle is 0. This can be expanded to a closed loop that consists of infinite number of Carnot cycles, as you can see in this plot. Suppose this single cycle is infinitesimally small. The sum of dq over t of all the Carnot cycles is 0. This can be expressed by cyclic integration of dq over t under a reversible condition equals 0. The reversible dq over t is ds. Consequently, the cyclic integration of ds is equal to 0, which is called Clausius equality, and this is a strong proof that entropy is a state function. Take note that the reversible dq over t is the thermodynamic definition of entropy. Refrigeration process is like reversing the process of a heat engine. Heat engine is a device that utilizes the spontaneous heat transfer from a hot source to a cold environment. On the contrary, a refrigerator is a device that removes heat QC from an object to the environment, keeping the object at low temperature TC, as this animation illustrates. The temperature of the environment is denoted by TH, while the temperature of an object inside a refrigerator is denoted by TC. Take note that reversing a spontaneous process is not spontaneous, which is not free at all. That is why you should pay the electric bill to keep your refrigerator running. The animation on the left can be simplified by this chart. Heat QC is removed from an object in the refrigerator and dumped into the environment. The question is this process spontaneous or non-spontaneous? We should find out the change of total entropy after the heat transfer. Delta S1 represents the entropy change in the environment, and delta S2 represents the entropy change in the refrigerator. The delta S1 is positive QC over TH. The sign should be positive because the environment gains heat QC. The delta S2 is negative QC over TC. The sign should be negative because the system or the refrigerator loses the same quantity of heat QC that the environment gains. The total entropy change is the sum of delta S1 and delta S2, which is QC over TH minus QC over TC. The QC can be factored out like this. Because TC is lower than TH, 1 over TH is less than 1 over TC, which leads to negative delta S total. This proves that the refrigeration is a non-spontaneous process. Be aware that work should be done to the refrigerator to overcome the entropy loss. The coefficient of performance of a refrigerator is defined as the quantity of heat removed from the refrigerator by the work done. It is expressed mathematically like the coefficient C equals absolute value of QC over absolute value of W. It is obvious when less work is required to achieve a given transfer of heat, the coefficient of performance becomes greater, and as a result, the refrigerator becomes more efficient. Because QC is removed from the refrigerator and the work W is added to the energy stream, the energy deposited as heat in the environment is QH equals QC plus W. The reciprocal of C is W over QC, which is equal to QH minus QC over QC. The mathematical expressions of QH and QC were derived at the Carnot cycle. Plug these into the equation, which leads to this. The NR and log VB over VA in the numerator can be factored out like this. The NR and log VB over VA are cancelled. Consequently, 1 over C is equal to TH minus TC over TH. It further implies that C equals TH over TH minus TC. It demonstrates that the coefficient of performance of a refrigerator can be expressed by TH over TH minus TC. It implies that the performance of a refrigerator is maximized when the temperature difference between TH and TC is minimized. Previously, Carnot cycle was used to demonstrate that the efficiency of a reversible engine can be expressed with respect to heat gain, QH, and heat loss, QC. It can also be expressed with respect to TH and TC. On the contrary, the efficiency of an irreversible engine cannot be expressed with respect to TH and TC. This is because the fraction TH minus TC over TH was the result from the two reversible isothermal processes in the Carnot cycle. The epsilon reversible is greater than the epsilon irreversible, and this relationship can be expressed like this. It can be rewritten as 1 minus Tc over Th is greater than 1 plus Qc over Qh. The number 1 is cancelled out, which leads to this. Rearrange T's and Q's, and it will lead to this. Negative QH over TH is greater than QC over TC. Move negative QH over TH to the right side. It leads to QH over TH plus QC over TC is less than 0. This whole process is an irreversible process. Suppose a multi-step process. If one step of the process is irreversible, while all other steps are reversible, then the whole process is considered as irreversible. It is summarized by this simple cyclic integration. The cyclic integration of dq over t of an irreversible process is always less than 0. The Clausius equality implies that the cyclic integral of dq over t for a reversible cycle is always equal to 0. How about the cyclic integral of dq over t for an irreversible cycle? It will lead to the Clausius inequality, and I will show you how the inequality is derived. The magnitude of the work done under a reversible condition is always greater than the magnitude of the work done under an irreversible condition. The dW of the system is negative here because it represents the work done by the system. That is why the negative sign is added in order to make it positive. Move the negative dW irreversible to the left side. Now, dW reversible minus dW irreversible is less than 0. Internal energy U is a state function, which implies that it does not depend on the path, whether the path is reversible or irreversible. So, du reversible is equal to du irreversible. This can be written as dq reversible plus dw reversible equals dq irreversible plus dw irreversible. Gather the dw terms on the left side of the equation and the dq terms on the right side of the equation. It can be done by moving dw irreversible to the left side of the equation and dq reversible to the right side. As you can see, these two are identical. This implies that dq irreversible minus dq reversible is less than 0. It further implies that dq reversible is greater than dq irreversible. Divide both dq reversible and dq irreversible by t. Take note that dq reversible divided by t is the thermodynamic definition of entropy. This implies that ds is equal to dq reversible over t, but it is less than dq irreversible over t. It can be combined to this simple expression. ds is equal to or greater than dq over t. This is called Clausius inequality. Heat transfer is blocked in an isolated system. Consequently, dq is 0. Apply this to the Clausius inequality. Then it leads to ds is always equal to or greater than 0 in an isolated system, which is the second law of thermodynamics. In an isolated system or universe, the entropy cannot decrease when a spontaneous change occurs. Entropy is not a physically measurable quantity, which means that we are unable to measure entropy directly using an experimental setup. Then, how do we determine the entropy of the system under a variety of conditions? The good news is that we can indirectly determine the entropy using other physically measurable properties. The internal energy change du can be expressed like this. du equals dq plus dw. In the previous chapter, it was proven that du equals TdS minus PdV. du is also equal to pi t dV plus Cv dt. Since the internal pressure pi t is 0 for a perfect gas, du is simply equal to Cv dt for a perfect gas. This implies that TdS minus PdV equals Cv dt. Move PDV to the right side of the equation. Use the equation of state of a perfect gas and replace pressure P with nRT over V. Divide both sides of the equation by T. This leads to ds equals nR over V times dV plus CV over T times dt. Now, check this equation. Like I said, ds that is on the left side of the equation is not a physically measurable quantity. On the contrary, all of the n, r, v, cv, and t on the right side of the equation are either constants or physically measurable properties. It shows that the ds that is physically unable to measure can be determined with physically measurable properties. Delta S is the integral from state 1 to state 2 ds. Replace ds with this and split it into two integrals like this. Since nr and cv are constants, they can be brought out of the integrals. Now finally, it should be like this. Delta S for a perfect gas is equal to nR times log V2 over V1 plus CV times log T2 over T1. Under an isothermal condition, T1 and T2 are the same. Since log 1 is simply equal to 0, delta S under an isothermal condition is equal to nR times log V2 over V1. On the contrary, under an isometric condition, V1 and V2 are the same. Consequently, delta S is equal to CV times log T2 over T1. Under an adiabatic condition, Q is equal to 0 because there is no heat transfer. As a result, ds is equal to 0. Likewise, delta S is also equal to 0. We can prove this using an alternative way. In the previous chapter, it was proven that TV to the power of gamma minus 1 is always the same at an adiabatic condition. So, T1V1 to the power of gamma minus 1 equals T2V2 to the power of gamma minus 1. We may rearrange T's and V's and make T2 over T1 equals V1 over V2 to the power of gamma minus 1. Plug this into the equation of delta S of a perfect gas. Replace T2 over T1 with V1 over V2 to the power of gamma minus 1. The exponent gamma minus 1 can be brought out of log like this. You may flip V1 over V2 like this by changing the sign of the second term from positive to negative. The log V2 over V1 can be factored out. Gamma is Cp over Cv, and plug this into the equation. Then, gamma minus 1 can be modified to a fraction, Cp minus Cv over Cv. As proven in Chapter 2, Cp minus Cv is equal to nR, and the fraction Cp minus Cv over Cv is turned into nR over Cv. The Cv is cancelled. Now, nR minus nR is 0, which makes delta S 0. So, utilizing an alternative method, delta S is also proven to be 0 under an adiabatic condition. Let's find out the total entropy change accompanying actual processes under a variety of conditions. The delta S total allows us to determine whether a process is spontaneous or non-spontaneous. Delta S total would be 0 for a reversible non-spontaneous change. On the other hand, delta S total would be greater than 0 for an irreversible spontaneous change. What is delta S total for the isothermal reversible expansion? Previously, the delta S of a perfect gas was derived as nR times log V2 over V1 plus Cv times log T2 over T1. T1 and T2 are the same at an isothermal condition. As a result, the delta S for the expansion is equal to nR times log V2 over V1. The entropy change of the system during the process is equal to Q system over T, which is also equal to nR times log V2 over V1. The entropy change of the surroundings is Q surroundings over T, which is equal to negative Q system over T. Take note that the heat gained by the surroundings is equal to the heat lost by the system. In other words, Q surroundings equals negative Q system. So, delta S of the surroundings is negative nR times log V2 over V1. Delta S total is equal to delta S system plus delta S surroundings, which is equal to 0. It implies that the isothermal reversible expansion is a non-spontaneous process. How about an isothermal irreversible free expansion against vacuum? Is it a spontaneous or a non-spontaneous process? To answer that question, we should find out the delta S total just like we did for the isothermal reversible expansion. Since it is an isothermal expansion, delta S system is equal to nR times log V2 over V1. The internal energy change delta U is always 0 for an isothermal process, which makes the sum of Q and W 0 as well. Since work is not done during the free expansion process, W equals 0 and Q is equal to 0 as well. Consequently, the heat transferred to the surroundings is 0. As a result, delta S surroundings is 0. This leads delta S total to nR times log V2 over V1. Since V2 is greater than V1 for the volumetric expansion, delta S total is greater than 0. It implies that the isothermal irreversible free expansion occurs spontaneously. How about the entropy change during a phase transition? At the temperature of phase transition, the heat transfer between the system and the surroundings is reversible. This is because the two phases in the system is in equilibrium. Delta S at the transition is equal to Q transition over T transition. The heat transferred during the phase change is the transition enthalpy. If the phase change is exothermic, like condensation from vapor to liquid, or freezing from liquid to solid, the delta H would be negative. Consequently, the delta S for those phase changes would also be negative. Negative delta S implies that the substance becomes more ordered after the phase change. A couple of examples are freezing and condensing. On the other hand, delta S would be positive if the transition enthalpy is positive. The positive delta S implies that the substance becomes less ordered after the phase change. A couple of examples are melting and vaporizing. Troughton's rule states that a wide range of liquid have approximately the same standard entropy of vaporization, which is about 85 joules per mole per Kelvin. It can be understood that a similar change in volume occurs when any liquid evaporates and becomes a gas. Therefore, all liquids can be expected to have similar standard entropies of vaporization. Exception to the Troughton's rule is the liquids that have strong intermolecular interactions like water. Water has strong intermolecular force called hydrogen bonding. As a result, the vaporization of liquid water leads to a greater dispersal of energy and causes higher standard entropy of vaporization. The standard molar entropy of vaporization of water is 118.92 joules per Kelvin per mole, which is substantially higher than the value predicted by Troughton's rule. Let's try a couple of practice problems. Prove that the phase transition of 0 Celsius ice to 0 Celsius water at 0 Celsius and 1 atm is a reversible, non-spontaneous process. The enthalpy of fusion of water is given as 6.008 kilojoules per mole. Whether a change occurs spontaneously or non-spontaneously depends on delta S total. The delta S total for a reversible, non-spontaneous change is 0. On the other hand, the delta S total for an irreversible spontaneous change is greater than 0, implying that the entropy of an isolated system increases during a spontaneous change. So, the first step in this problem is to identify the system and the surroundings. If you identify them incorrectly, you are most likely to end up with the wrong answer. The next step is to determine delta S system, delta S surroundings, and delta S total. Now, what is the system and the surroundings in this problem? Obviously, the system is the ice, and the surroundings are everything else. The delta S system is Q system over T, and the heat transferred to the system, that is Q system, is equal to the enthalpy of fusion of water. The delta H fusion is 6.008 kilojoules per mole, and the temperature of ice is 0 Celsius. Plug these into the equation. Convert energy unit kilojoule to joule and temperature unit Celsius to Kelvin. This leads to 22.0 joules per Kelvin per mole. It implies that as the ice melts to liquid water, the entropy increases and the degree of randomness increases as a result of it. The delta S surroundings is Q surroundings over T. The temperature of the surroundings is 0 Celsius. Q surroundings is equal to negative Q system based on the first law of thermodynamics, or the law of energy conservation. Consequently, Q surroundings is equal to negative enthalpy of fusion over T, and it is negative 22 joules per Kelvin per mole. The delta S total is the sum of delta S system and delta S surroundings, which is equal to 0. This confirms that the phase transition of 0 Celsius ice to 0 Celsius water at 0 Celsius and 1 atm is a reversible, non-spontaneous process. Let's try another practice problem. Prove that the phase transition of 0 Celsius ice to 0 Celsius water at 20.0 Celsius and 1 atm is an irreversible, spontaneous process. Not like the previous problem, the temperature of the surroundings is 20.0 Celsius. All other conditions remains unchanged. The delta S system is exactly the same as the one in the previous problem, which is 22.0 joules per Kelvin per mole. However, the temperature of the surroundings is 20.0 Celsius. The delta S surroundings is negative delta H fusion over T. the T is 20.0 Celsius or 293.15 Kelvin. This leads to delta S surroundings being negative 20.5 joules per Kelvin per mole. The delta S total is the sum of delta S system and delta S surroundings, which is equal to 1.5 joules per Kelvin per mole. The positive value of delta S total implies that the phase transition of 0 Celsius ice to 0 Celsius water at 20.0 Celsius and 1 atm is an irreversible, spontaneous process. Suppose a substance is heated from low temperature to high temperature. While it is heated, it may go through phase transitions. How do we determine the overall change in entropy from the beginning to the end of the heating process? Assume that the pressure is kept constant and there is no expansion work involved in this heating process. When the substance is heated through variable temperature region before getting into a phase transition, the entropy change of the substance from T1 to T2 is integral from T1 to T2 dq reversible over T. The dq reversible is equal to Cp dt. The heat capacity at constant pressure Cp is assumed to be constant and it can be brought out of the integral. Consequently, the delta S of a substance heated from T1 to T2 is equal to Cp times log T2 over T1. On the other hand, we should determine the delta S of a substance when it is heated through a constant temperature region like a phase transition. For instance, boiling of water occurs at a constant temperature, that is 100 Celsius. If we use the equation on the left, the delta S is calculated to be 0, which does not make any sense at all, because the vaporization of liquid water increases the level of randomness of the water molecules. So, we should use a different equation. Delta S is equal to Q reversible over T. The heat transferred during a phase transition is called transition enthalpy. So the delta S at the phase transition is transition enthalpy over T. Let's try a practice problem. Calculate the change of entropy for the heating process from negative 10.0 Celsius ice to 120.0 Celsius vapor. The Cp of ice is 37.66 joules per Kelvin per mole. The Cp of water is 75.32 joules per Kelvin per mole. And the Cp of water vapor is 33.58 joules per Kelvin per mole. The standard fusion enthalpy of ice is 6.008 kilojoules per mole, and the standard vaporization enthalpy of water is 40.656 kilojoules per mole. Here is a generalized entropy temperature plot, and I want to talk about it before handling the practice problem. The capital S at 0 Kelvin represents the entropy of a substance at absolute zero. This blue dot represents the entropy of the substance at the final temperature Tf. As the temperature increases from 0 Kelvin to a low temperature TL, the entropy of the substance also increases. Be aware that the substance is heated along a variable temperature region. So, the entropy of the substance at a temperature TL is equal to initial entropy at 0 Kelvin plus integral from almost 0 Kelvin to TL Cp dt over T. The entropy change caused by the heating from TL to melting point of the substance Tmp is shown in this curve, which is denoted by delta S1, and it is equal to integral from TL to Tmp Cp dt over T. You may ask a question why these two heating regions are not combined, even if the substance is in solid phase in both regions. It is because the heat capacity of a solid at a cryogenic temperature is most likely a function of temperature rather than a constant, while the heat capacities of the substance in solid, liquid, and gas phases at relatively high temperatures are taken as constants. Consequently, the Cp of a substance at a cryogenic temperature cannot be brought out of integral. The entropy of the substance increases when it undergoes the phase transition from solid to liquid, even if temperature is fixed to its melting point. The entropy change of the substance in this constant temperature region is denoted by delta S2, and it is equal to the fusion enthalpy of the substance over T. The substance is being heated past its melting point. The entropy change in this variable temperature region is denoted by delta S3, and it is equal to integral from Tmp to Tbp Cp dt over T. The substance boils at its boiling point and undergoes the phase transition from liquid to gas. As you can see, the temperature is fixed to Tbp. The entropy change in this constant temperature region is denoted by delta S4, and it is equal to the vaporization enthalpy of the substance over T. The substance is being heated past its boiling point until the temperature gets to the final temperature Tf. The entropy change in this variable temperature region is denoted by delta S5, and it is equal to integral from Tbp to Tf Cp dt over T. The entropy final of the substance is simply the sum of these entropies, and it is equal to STL plus delta S1 plus delta S2 plus delta S3 plus delta S4 plus delta S5. This generalized heating curve can be modified specifically for the practice problem, and it should look like this one. Be aware that temperature unit should be converted to Kelvin, and energy unit should be converted to a single unit, either joule to kilojoule or kilojoule to joule. There are three variable temperature regions, and the entropy changes at the regions are represented by delta S1, delta S3, and delta S5. The Cp value of each phase, solid, liquid, or gas, is given in the problem. There are two constant temperature regions, and the entropy changes in the two regions are represented by delta S2 and delta S4. The enthalpies of fusion and vaporization of water are also given in the problem. The overall entropy change in the course of heating -10 C ice until it becomes 120.0 Celsius water vapor is the sum of these entropies, and the sum is 157.60 joules per Kelvin per mole. Don't forget to convert Celsius to Kelvin and make energy units consistent. All energy of thermal motion is quenched at absolute zero. As a result of it, all the atoms or ions in a perfect crystal form a uniform single array. Due to the presence of this one microstate, the entropy of all perfect crystalline solids is zero at absolute zero, which is the essence of the third law of thermodynamics. It is experimentally observed and summarized by the Nernst heat theorem. This is an entropy temperature plot. Under low pressure and temperature, sulfur forms two distinctive crystalline structures, orthorhombic, which is also called alpha sulfur, and monoclinic, which is also called beta sulfur. What should be noted is that at 369 Kelvin, sulfur undergoes a phase transition from beta sulfur to alpha sulfur. The entropy change at this beta to alpha transition is the molar entropy of the alpha sulfur minus the molar entropy of the beta sulfur. Keep in mind that delta represents final value minus initial value. There are two approaches to determine the delta S at the transition. The first method is to utilize the enthalpy of phase transition. The delta H for the beta to alpha transition of sulfur is known to be negative 402 joules per Kelvin per mole at 369 Kelvin. Then the delta S for the transition is equal to delta H for the transition over T, which leads to negative 1.09 joules per Kelvin per mole. Negative delta S implies that the solid sulfur becomes more ordered as it undergoes the beta to alpha transition at 369 Kelvin. Keep this delta S value in mind. The second method is to utilize the heat capacities of the two forms of sulfur. As temperature decreases down to absolute zero, the entropy of alpha sulfur decreases, which is illustrated by the cyan curve in the plot. Then the molar entropy of alpha sulfur at 369 Kelvin is equal to the molar entropy of alpha sulfur at 0 Kelvin plus integral from 0 Kelvin to 369 Kelvin molar Cp of alpha sulfur dt over T. As temperature decreases down to absolute zero, the entropy of beta sulfur also decreases, which is illustrated by the blue curve in the plot. The molar entropy of beta sulfur at 369 Kelvin is equal to the molar entropy of beta sulfur at 0 Kelvin plus integral from 0 Kelvin to 369 Kelvin molar Cp of beta sulfur dt over T. The delta S for the transition is simply the difference between the two molar entropies, which turns out to be the molar entropy of alpha sulfur at 0 Kelvin minus the molar entropy of beta sulfur at 0 Kelvin minus 1 joule per Kelvin per mole. The delta S for the transition that was determined using the two approaches should be the same in theory. The negative 1.09 joules per Kelvin per mole in the first approach is pretty close to negative 1 joule per Kelvin per mole in the second approach. For this to be valid, the difference between the molar entropy of alpha sulfur and the molar entropy of beta sulfur should be zero. This experimental observation is summarized by the Nernst heat theorem, and it states the entropy change accompanying any physical or chemical transformation approaches zero as the temperature approaches zero, provided all the substances involved are perfectly crystalline. It provides experimental support for the third law of thermodynamics, stating the entropy of all perfect crystalline substances is zero at absolute zero. Entropy is defined statistically by Boltzmann's formula, which is S equals K times log W. Like I said in the previous slide, all energy of thermal motion is quenched at absolute zero. As a result of it, all the atoms or ions in a perfect crystal form a uniform single array, creating only one microstate at absolute zero. Plugging this to the Boltzmann's formula leads to entropy being zero. It implies that the entropy of a perfect crystalline compound is zero at 0 Kelvin. On the contrary, there may be almost no energy difference for a diatomic molecule between two types of molecular arrangements like AB, 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 and BA, BA, BA. In such circumstance, there are more than one microstates at absolute zero, leading to entropy being greater than zero. Non-zero positive entropy of molecular solids at absolute zero is called residual entropy. Entropies reported on the basis of the third law of thermodynamics is called third law entropies. The standard third law entropy, or simply standard entropy of a substance, is denoted by capital S naught. And a list of standard entropy values at 298 Kelvin can be found at the back of the textbook. Standard entropies of substances can be used to determine the standard reaction entropies, which is equal to the sum of the standard entropies of products minus the sum of the standard entropies of reactants. The nu and nu prime are the stoichiometric coefficients of products and reactants in a reaction. Take note of a couple of things about the standard entropy. First, the standard entropy of H plus ion in water is taken as zero at all temperatures. And second, the standard entropies of elements are not zero. In order to identify the direction of a natural change or a spontaneous change, we should calculate the total entropy changes of both the system and the surroundings. In other words, we should analyze the changes in the surroundings as well as in the system. The thing is, it would be a lot easier if we could focus only on the change of the system in identifying the direction of a spontaneous change without worrying about what is happening in the surroundings. The good news is that the Helmholtz free energy and Gibbs free energy allow us to focus our attention on the system, and I will show you how it is done. Like I said in the beginning of chapter 2, the universe is an isolated system where it does not exchange energy or matter with its surroundings. The second law of thermodynamics states that the entropy of the universe never decreases and always increases for a spontaneous change, which is represented by this simple expression. We know that delta S universe is the sum of delta S system and delta S surroundings. If T remains constant, it can be multiplied to both sides of the equation. Be aware that T represents temperature on an absolute scale and cannot be negative. If delta S universe is equal to or greater than 0, so is the T delta S universe. Here, delta S surroundings is equal to Q surroundings over T, which is also equal to negative Q system over T. Now, T times delta S surroundings is simply negative Q system. Plug this to the equation on the left. This leads to T delta S system minus Q system is equal to or greater than 0. This can be re-expressed as Q minus T delta S of the system is equal to or less than 0. We started with the changes of entropies of both the system and the surroundings, but now we ended up with the change of the system only, and we don't have to worry about the change of the surroundings anymore. And I will show you how this relation is developed for either Helmholtz free energy or Gibbs free energy in the next slide. What are the criteria for a process to be spontaneous? In the previous slide, we proved that Q minus T delta S of the system cannot be positive for a process in nature. We will develop this inequality under the conditions of constant volume and constant pressure. At constant volume with no additional work other than expansion work, the inequality can be written as Q sub V minus T delta S is less than or equal to 0. For an infinitesimal change, it can be written as dQV minus TdS is less than or equal to 0. Since the heat transferred at constant volume is the same with the change of internal energy, the expression can be modified to du minus TdS is less than or equal to 0. If both the entropy and volume are kept constant, then TdS becomes 0, and only du survives, leading to du at constant entropy and volume is less than or equal to 0. On the other hand, if both the internal energy and volume are kept constant, then du becomes 0, and only negative TdS survives, leading to ds at constant internal energy and volume is greater than or equal to 0. If the temperature is maintained constant, SdT is 0. So you can subtract it from either side without affecting the inequality like this one. du minus TdS minus SdT is less than or equal to 0. You may combine the expression as du minus Ts is less than or equal to 0. The Helmholtz energy, capital A, is defined as U minus Ts. Consequently, the criteria for a spontaneous change at constant T and V is that the dA of the change should be less than 0. Take note that dA should be 0 for a reversible non-spontaneous equilibrium process at constant temperature and volume. dA can be written as du minus Tds. At constant pressure with no additional work other than expansion work, the inequality can be written as Q sub P minus T delta S is less than or equal to 0. For an infinitesimal change, it can be written as dQp minus TdS is less than or equal to 0. Since the heat transferred at constant pressure is the same with the change of enthalpy, the expression can be modified to dH minus TdS is less than or equal to 0. If both the entropy and pressure are kept constant, then TdS becomes 0, and only dH survives, leading to dH at constant entropy and pressure is less than or equal to 0. On the other hand, if both the enthalpy and pressure are kept constant, then dH becomes 0, and only negative TdS survives, leading to ds at constant enthalpy and pressure is greater than or equal to 0. If the temperature is maintained constant, SdT is 0, so you can subtract it from either side without affecting the inequality like this one. dH minus TdS minus SdT is less than or equal to 0. You may combine the expression as dH minus Ts is less than or equal to 0. The Gibbs energy, capital G, is defined as H minus Ts. Consequently, the criteria for a spontaneous change at constant T and P is that the dG of the change should be less than 0. Take note that dG should be 0 for a reversible non-spontaneous equilibrium process at constant temperature and pressure. dg can be written as dH minus TdS. There is a misconception about Helmholtz free energy. As proven in the previous slide, the criteria for a change to be spontaneous at constant temperature and volume is that the change of Helmholtz free energy, dA, should be negative. Another thing to be noted is that dA should be 0 for a reversible, non-spontaneous equilibrium process. Here, dA is equal to du minus TdS, which should be negative for a spontaneous change. The question is, how do we make this quantity du minus TdS as negative as possible so that the change becomes as spontaneous as possible? It seems obvious that the du should be as negative as possible, and because of the negative sign in front of TdS, the ds should be as positive as possible, which would lead to dA being as negative as possible. This would create a misconception about the criteria for spontaneity of a change, like du should always be negative. This is not correct because there are spontaneous processes with positive du, even if there are numerous spontaneous processes with negative du. The same goes for the change of entropy, ds. Keep it in mind that the expression du minus TdS originates from the idea that ds total should always be positive for a spontaneous process. So the focus should not solely be on the du or TdS, but rather it should be on the change in total entropy. The change in the Helmholtz free energy, delta A, is equal to the maximum work that the system can do, and I will prove it in this slide. The Clausius inequality states that the total entropy of an isolated system can never decrease in a spontaneous process, and it can be expressed as ds is greater than or equal to dq over t. It can be rewritten as TdS is greater than or equal to dq. We can combine it with the first law of thermodynamics, dq plus dw equals du. It implies that TdS plus dw is greater than or equal to du. Move the TdS to the right side, which will be dw is greater than or equal to du minus TdS. Be aware that dw is the work done by the system, and as a result, it should be negative. Consequently, the most negative work done by the system is when dw becomes equal to du minus TdS, which is dA. For a macroscopic change, the maximum work is equal to delta U minus T delta S, which is also equal to delta A. This equation exhibits that in some cases, not all the delta U may be available for the system to do work, which depends on the sign of delta S. Here are two possible scenarios that we can think of. The first case is where the entropy of the system decreases as the system does work on the surroundings. On the contrary, the second case is where the entropy of the system increases as the system does work on the surroundings. Take note that the delta U in both cases decreases, and this is because the system in both cases loses energy by doing work on the surroundings. Let's focus on the left case where the entropy decreases. The maximum work done by the system is written as delta A, which is equal to delta U minus T delta S. The sign of delta U is negative, and the sign of the second term negative T delta S is positive because delta S is negative. And we know that delta A is negative because the system does work on the surroundings. It is obvious that both delta A and delta U are negative. The question is, which one is more negative? Think about this. The positive quantity, the negative T delta S, is added to the negative quantity delta U to make overall negative quantity delta A. Which one do you think more negative, delta A or delta U? Pause the video and think about it for a minute. The answer is delta A is less negative than delta U. It implies that the absolute value of the work is less than the absolute value of delta U. In other words, the system does work less than the change of internal energy delta U. What happens to the remaining energy? Well, the remaining energy escapes the system in the form of heat. It implies that the system should lose the heat Q in order to do work on the surroundings. It is like nature demands a tax on the internal energy as it is converted into work. Since the surroundings gain the heat Q, the entropy of the surroundings increases. In summary, for the change to be spontaneous, some of the energy must escape as heat in order to generate entropy in the surroundings to overcome the reduction in the entropy of the system. Let's move to the next case where the entropy of the system increases as the system does work on the surroundings. Check the same equation that we used for the first case. The sign of delta U is negative, and the sign of the second term, negative T delta S, is negative overall because delta S is positive, and delta A is negative because the system does work on the surroundings like the first case. Both delta A and delta U are negative. Which one is more negative, delta A or delta U? Think about this. The negative quantity, that is, the negative T delta S, is added to the negative quantity delta U to make overall negative quantity delta A. Which one do you think more negative, delta A or delta U? Pause the video and think about it for a minute. The answer is delta A is more negative than delta U. It implies that the absolute value of the work is greater than the absolute value of delta U. In other words, the system does work more than it can afford. How can this happen? Well, the heat Q transferred into the system from the surroundings. It implies that the system does work more than delta U by gaining additional heat from the surroundings. It is like nature provides a tax refund. Since the surroundings loses the heat Q, the entropy of the surroundings decreases. In summary, energy flows in as heat as work is done and contribute to the work that the change is generating. The significance of Helmholtz free energy lies in the fact that delta A is part of delta U that we are free to use to do work. At constant pressure and temperature, the Gibbs free energy of a spontaneous reactions decreases. It implies as the delta G of a reaction becomes more negative, the reaction becomes more spontaneous. How do we make the delta G more negative? Here, we are facing the same argument as we did with the Helmholtz free energy. In order to make delta G more negative, the delta H should be more negative and delta S should be more positive. This creates a misconception like the delta H of a spontaneous reaction should always be negative. but it is not correct because there are spontaneous endothermic reactions with positive delta H, even if there are numerous exothermic spontaneous processes with negative delta H. One example is the dissolution of ammonium chloride in water. When it is mixed with water, the temperature of the solution decreases, implying that the spontaneous dissolution process is endothermic and makes delta H positive. In fact, the ammonium chloride is the key ingredient of a cool pack. How come the increase of enthalpy drives the reaction spontaneous? The thing is, as heat flows into the system, the entropy of the system increases, and it would cause T delta S to outweigh delta H, leading to negative delta G. In the previous slide, it was proven that delta A is the maximum work that the system can do on the surroundings. On the other hand, delta G is the maximum non-expansion work that the system can do at constant pressure and temperature. And I will prove it in this slide. In Chapter 2, enthalpy was defined as U plus PV. The derivative of enthalpy can be written as du plus dPV. Use the product rule to dPV, and it should written out as VdP plus PdV. Since it is under the condition of constant pressure, the dP becomes 0. This simplifies the equation to dH equals du plus PdV. The mathematical expression of the first law is du equals dQ plus dW. The work that the system does on the surroundings can be associated with the volumetric expansion of the system, which is denoted by dW expansion. On the contrary, the work that the system does on the surroundings may have nothing to do with the volumetric expansion of the system, which is denoted by dW non-expansion. dW expansion is equal to negative PdV. Plug this into the equation on the left. PdV is cancelled, which leads to dQ plus dW non-expansion. The mathematical expression of the second law is ds equals dQ over T. This can be modified to dQ equals TdS. Plug this into the equation on the left, which leads to TdS plus dW non-expansion. Move TdS to the left side of the equation. Since it is at constant temperature, dt is 0, and so is SdT. So adding the negative SdT to the left side of the equation does not affect the equality. The left side of the equation can be combined to dH minus Ts. The H minus Ts is the definition of Gibbs free energy. So dG is equal to dW non-expansion, or delta G is equal to W non-expansion. It proves that delta G is the maximum non-expansion work at constant pressure and temperature. Examples of non-expansion work are magnetic work and electrochemical work, which do not involve volumetric expansion. You will encounter delta G frequently when you study electrochemistry. There are a couple of ways to determine the standard reaction Gibbs free energies. If you are given with the information like the standard reaction enthalpy, the standard reaction entropy, and the temperature of a reaction, you can simply plug them into this equation. Take note that you can determine the standard reaction enthalpy and the standard reaction entropy by utilizing the standard formation enthalpies and the third law entropies of reactants and products that are provided at the data section at the end of the textbook. The data section also provides the standard formation Gibbs free energies of reactants and products. You can utilize them to find the standard reaction Gibbs free energy of a reaction. The standard reaction Gibbs free energy of a reaction is equal to the sum of the standard formation Gibbs free energies of products minus the sum of the standard formation Gibbs free energies of reactants. The nu and nu prime are the stoichiometric coefficients of products and reactants in the reaction. Take note of a couple of things about the standard formation Gibbs free energy. First, the standard formation Gibbs free energies of elements in their reference states are all zero. And second, the standard formation Gibbs free energy of H plus ion in water is also taken as zero. Pressure and temperature are important for discussing phase transitions and chemical reactions. Then, how would the Gibbs free energy vary with pressure and temperature? In Chapter 2, we have proven that dG can be expressed as VdP minus SdT. Here is the function Gibbs free energy that has two variables, pressure and temperature. The total differential of G can be written like this. The total differentials of variety of functions were covered in Chapter 2. So, if you are not quite sure about the total differentials, please check the Chapter 2 video and class notes. Compare the two differentials side by side. It is obvious that the first partial derivative of G with respect to t at constant p is equal to negative s, and the first partial derivative of G with respect to p at constant t is equal to v. Focus on the left one. We learned previously that as temperature increases, the entropy of all substances increases as well. The entropy should be positive, but because of the negative sign in front of S, the slope dG over dt should be negative. In other words, as temperature increases, the entropy of a substance also increases, but the Gibbs free energy decreases. The entropy of solid is the least. The entropy of liquid follows next, and the entropy of gas is the greatest. The slopes in the plot, G versus T, are all negative. The least negative for solid, but most negative for gas. Liquid stays in the middle. Here is a plot, G versus T. The entropy of the liquid phase of a substance is more positive than the entropy of the solid phase. It implies that the slope of the liquid phase is more negative than the slope of the solid phase. The crossover point of the two lines represents the freezing point of the substance. The entropy of the gas phase of the substance is more positive than the entropy of the liquid phase. It implies that the slope of the gas phase is more negative than the slope of the liquid phase. The crossover point of the two lines represents the boiling point of the substance. What is the most stable phase of the substance below its freezing point? As you can see in the plot, the phase with the most negative Gibbs free energy is solid. That is why all substances below their freezing points freeze spontaneously. What is the most stable phase of the substance at a temperature between its freezing point and boiling point? Check the plot again. The phase with the most negative Gibbs free energy is liquid in this range. That is why the substance at a temperature between its freezing point and boiling point melts spontaneously from solid phase or condenses spontaneously from vapor phase. What is the most stable phase of the substance above its boiling point? As you can see in the plot, the phase with the most negative Gibbs energy is gas. That is why all substances above their boiling point vaporize spontaneously. Let's move to the slope on the right. The first partial derivative of G with respect to P at constant T, which is equal to V. Since the volume of all substances are positive, Gibbs free energy always increases as pressure increases at constant temperature and composition. The molar volume of gas of a substance is substantially greater than the molar volume of liquid of the substance, and the molar volume of liquid is slightly greater than the molar volume of solid. Of course, water is an exception because the molar volume of ice is greater than the molar volume of liquid water, which is due to the presence of strong hydrogen bonding. But what I am talking about here is substances in general. We can sketch this trend in the plot G versus P. Because the derivative dG over dP increases with V, the Gibbs free energy becomes more sensitive to pressure when the volume of the substance is large. In other words, because the molar volume of the gas phase of a substance is greater than the molar volume of condensed phases like liquid and solid, the molar Gibbs free energy of a gas becomes more sensitive to pressure than its liquid and solid phases. The equilibrium composition of a chemical system depends on the Gibbs energy, and chemical equilibrium is also affected by temperature. So that is why we need to understand how Gibbs energy varies with temperature. One well-known equation that shows the temperature dependence of Gibbs energy is called Gibbs-Helmholtz equation, and I will show you how the equation is derived. Gibbs energy G is defined as H minus Ts. This equation can be modified with respect to negative S, which is G minus H over T. In the previous slide, it was proven that the first partial derivative of G with respect to T at constant P is equal to negative S, which is also equal to G minus H over T. You may split the fraction into G over T minus H over T. Move the G over T to the left side of the equation. Now, find the first partial derivative of G over T with respect to T at constant P. Keep it in mind that G is a function of T. Apply the product rule for derivatives, which leads to 1 over T times dG over dt minus G over T squared. Factor out 1 over T, and it will be 1 over T times dG over dt minus G over T. Now, dG over dt minus G over T can be replaced by negative H over T, which leads to negative H over T squared. This newly derived equation is called Gibbs-Helmholtz equation. The Gibbs-Helmholtz equation can be modified to this equation if delta G and delta H values are given. The Gibbs-Helmholtz equation can be applied to a chemical reaction. Here is a generic chemical reaction. Capital A and capital B represent reactants, and capital C and capital D represent products. Lowercase a, b, c, and d are stoichiometric coefficients. In order to find how the Gibbs free energy is affected by the change of temperature, we will use the Gibbs-Helmholtz equation. Delta H is assumed to be a constant within the temperature range. Move dt on the left side of the equation to the right side, which leads to d delta G over T equals negative delta H over T squared dt. Integrate both sides of the equation with respect to the temperature from T1 to T2. The delta H can be brought out of the integral because it is a constant. Finally, you will get this derived equation. The delta H is a constant value, and if delta G at T1 is a known value like the one at the standard state, then you can mathematically calculate delta G at any temperature T2 thanks to this equation. How would Gibbs free energy vary with pressure at constant temperature? Previously, it was proven that the first partial derivative of G with respect to P at constant T is equal to V. Move the dP to the right side, and it will be dG equals V dP. You can divide both sides by moles, and the equation will be converted into the one for molar quantity. Integrate both sides of the equation with respect to the pressure from P1 to P2. The integration on the left side will be the molar Gibbs energy at P2 minus the molar Gibbs energy at P1. Move the second term on the left to the right side of the equation. This derived equation will be used differently depending on whether we are dealing with gas or condensed matters like solid and liquid. We will adopt this equation for condensed phases. The molar volume of a condensed phase does not change significantly as pressure changes. So, it can be brought out of the integral, which leads to the molar Gibbs energy at P1 plus Vm times P2 minus P1. Under the normal laboratory condition, pressure would not change significantly. Consequently, the molar Gibbs energy of a condensed phase remains almost the same during day-to-day pressure fluctuations in the lab. However, in case that we cannot neglect the influence of change of pressure, and if the density of solid or liquid is known, we should approach the case differently. The density of a substance, ρ, is mass over volume. The mass of the substance is equal to its molar mass times moles. Move the moles in to the denominator. Then, volume over moles turns into molar volume, V sub m. Now, the molar volume of the substance can be expressed as molar mass over density. Plug this into the relation above, which leads to the molar Gibbs energy at P2 equals the molar Gibbs energy at P1 plus P2 minus P1 times molar mass over density. How about gases? Not like a condensed phase, the molar volume of a gas changes significantly as pressure changes. We will use the same equation that we used for a condensed phase. Suppose the gas behaves as a perfect gas. Use the equation of state for a perfect gas and replace the molar volume with RT over P. Since it is under the condition of constant temperature, RT is a constant as a whole and can be brought out of the integral. Now, the molar Gibbs energy at P2 can be written as the molar Gibbs energy at P1 plus RT times log P2 over P1. If the initial pressure P1 is the same with the standard pressure, and if the final pressure is denoted by P, then the equation can be written like this one.